Yes, now you can start, Professor.
Thank you so much, Vijay. Then let me start with a greeting. Good morning, good afternoon, good evening to everyone, depending on where you are. And then let's start the presentation. And today we will visit four domains of cyber physical system development. And the first block will be about the fundamentals and practicalities of controlling cyber physical systems. I might imagine that there are colleagues who are specializing themselves in control technologies and control solutions. I apologize if I'm telling them something what they well know already, but maybe for those of this overview of the field of fundamentals and practicalities of cyber physical system control may turn out to be useful in the end. So let me start my presentation with a forecast. And I say that open loop control will probably play an important role in in system level control of smart cyber physical systems. And the whole the presentation in this blog is dedicated to explain why I'm saying it. I will even bring up some industrial example in the second part of my presentation. So let's start with an overview of the control systems. Obviously, we know that controls means measuring selected variables of a system and adjusting the system to the correct limit, correct limit, the deviation of the, sorry, there is a typing error here, I apologize for that. So measuring the selected variables, and based on what we have measured, we try to regulate the system to work according towards the desired value. But disturbance is often occurring here, which can be also an error, but this is always a kind of unwanted input of the system. And disturbances are appearing as signals that are adversely affect the value of the system. So the output will not be that one what is expected. If a disturbance is generated within the system, then we refer to it as internal disturbance. And it can happen, for instance, based on the change of the law. If the disturbance is generated outside, then we consider it and handle it as as an external disturbance, and typically we associate it with some sort of internal disturbances. A control system, a device, a set of devices, can regulate itself and controls the operation of the system as a whole. Now, the main issue is that these control principles are very well known for traditional systems, but how about controlling smart cyber physical systems, especially systems which are equipped with the capabilities of problem solving? So how to control this system? This is a question what we are looking a answer to. So the basis of control. Actually, when we are talking about control, we have to separate three domains which are identified. One is the so-called model-based control. The second is the data-driven control. And just compare these two, model-based control is working based on a predefined model typically. It even gives a kind of feedback regulation or provides feed-forward regulation, open system, closed system, and it works with a kind of behavioral simulation, and this way gives some opportunity to see into the very near future. The data-driven control is actually based on the opportunity of data simulation, and the data are runtime assessed, and based on this, it is assumed that some sort of adaptation strategy is developed. And then it can be used for the behavior forecasting. Then when these two are combined, then we are talking about hybrid control. Hybrid control usually works with runtime adapter model. It applies some sort of intervention strategy based on which it invades into real life processes. And it often used feed-forward regulation, but currently this idea is questioned. And here the major output is the behavior estimation. So obviously, if we are talking about control, then we need controllers. And controller is a device that gets inputs from sensors and sends output to actuators and to central units. There are some major types of known controllers, for instance, programmable logic controllers, often referred to with the acronym PLC, then the distributed control system, DSC, and programmable automation controller, PACs. Controllers evolved over the time to a point where they can be utilized interchangeably with the removal of technological limits that determine their design choices, for instance. So it means that we have a plethora of different controllers to choose from, and obviously we have to always take into consideration if they provide the required functionality for our purpose. So even there are not just industrial controllers, but also so-called microcontrollers on the market. And microcontrollers, many of you know them, Raspberry, Arduino, and so on and so on, are very useful means to learn the fundamentals of control technology and also to develop a small-scale practical application. Nowadays, it is already possible to make conversions. For instance, a Raspberry Pi can be converted to a PLC if you use the open PLC application for this purpose. So these low-cost applications, I believe, are also important to consider in the development of cyber-physical systems. The next thing what I would like to elaborate on is the type of control structures. The control structure forms a whole horizon from predefined to prognostic. And this domain is this domain, which is called the control continuum, is populated by several control structures. For instance, we can identify decentralized or centralized control systems, and then hierarchical control systems, and then network control systems. And as we see, in fact, we are going towards a kind of decentralization and a less definitive type of operation. And then we have the distributed control systems, we have the multi-agent control system. And then if we consider that in addition to this axis based on which we could identify the 5 different approaches, we can also differentiate control structures based on if they are approaching or striving after optimal control or predictive control. From the next generation cyber physical system, I must tell you, and this will be my example later on all about, predictive control is more important than, for instance, just pure optimal control. So there is a huge development already in the industry, and there are so-called industrial control systems. ICS is actually a common term to refer to control systems such as the SCADA, the supervisory control and data communication, then the distributed control systems, and the peer programming logic controller systems, what we mentioned or what I mentioned earlier. So different industrial sectors use different control systems. And One of the major issues currently in the industry is the so-called cyber attack, which is against these well-set control systems, and if it happens, then these attacks may result in a devastating impact. So the reason for it is that the industrial control systems were gapped while running proprietary protocols, therefore less sensitive and less ready to correct things. Nowadays, however, the industrial control systems have been adapted to the changes, and this is obviously was needed by the proliferation of the Industry 4 concept. Most of the today's industrial control systems are integrated strongly with the industrial wireless sensor network or industrial IoTs, Internet of Things, and the new generation of programming logic controllers that evolves them into so-called advanced industrial cyber physical system support. SCADA DCS have converged together, allowing the implementation of hybrid systems that address new challenges. Security management, however, is still a key point for the industrial control systems, which are guided by national and regional organizations. Their development is guided by these national and regional organizations like the NIST in the United States. The next topic to discuss is the functional organization of industrial control systems. Here is a figure, a well-known figure from the internet, but it is very good because it is simple and related to the production world. Shows that sort of hierarchy which is general enough to be applied in several cases. You can see a kind of stratification. There are various levels defined here. The lowest level, level 0, is the field level. Then the second one, the level 1 actually, is the direct control level. Then the second 2 is the plant supervisory level. And then the level 3 is the production control. And the level 4 is the production scheduling level. So everything is organized around some sort of central computer or computer center. And there are coordinating computers included. They are the masters or some forms of supervisory computer, and these are connected or control microcontrollers. And these microcontrollers introduce changes or control into the plant operation, no matter how many plants are included. Obviously, this hierarchical structure represents just a kind of centralized solution. Nowadays, much more sophisticated, distributed, and parallelized architectures are also available as functional organizations of industrial control systems. What's important for us to see that most of the industrial control systems are based on the closed loop control assumption. It means that we talk about a closed loop control when the control action is dependent on the output of the system and state estimator is involved. In case of open loop control, there are no state estimator, and for instance, the control action doesn't depend on the actual output, just on the possibility. Closed loop control systems are suitable for for most of the complex CPS applications which do have definitive output. This is a questionable point because many systems actually do not have this definitive output. The use sensors and state estimator produce estimation and representation of the state variable. The control software generates control commands based upon the differences between the estimated and the desired values can be found and set. The measured operational values are compared to the desired values in various ways. For instance, one particular operational variable can be chosen, maybe the most critical, and compared with the output, or it can be aggregated and a kind of statistical average can be compared with the output, or it can be, for instance, or focusing on a exceptional deviation when one particular outlier is compared to the expected output. If you want to move further with or want to learn more related to closed-loop control systems, then I can encourage you to do so because actually the literature is representing a warehouse of many studies which are talking about the opportunities, the application, and the benefits of closed control loop. Also from a theoretical and practical perspective. So if we are talking about a closed loop, then we can create a kind of general model which is typically applied in first generation CPS. This model includes obviously the cyber-physical system and the input variables and the output variables. The output variables are supposed to be controlled. Then we have the disturbance here, and then a kind of regulatory mechanism is involved, which is typically working with some sort of reference signal. I apologize. And then this regulatory mechanism is processing the measured output and produce a control input, which is introduced into the control subsystem of the final of the first generation cyber physical system. So if we are talking about controllers, then we can identify certain types of the common controllers. For instance, we have so-called naive controller, which is actually just integrated or synergic part of the operating elements of a system setup, and it assumes a specific physical relationship between the input and output and introduces the changes accordingly. So for instance, let me take a very simple example, a electric motor which depends on the input energy and the output energy, the RPM is formed accordingly. So here, if I want to change the RPM, then I change the input energy, the voltage, the more specifically. Then we can have proportional controller, and the proportional controller introduces changes scaled to the output changes. So if there is a big error in the output, then it initiates a big adjustment in order to achieve a faster rise and reduce the overshoot of that particular signal or parameter what is going to control. Then we have the proportional derivative controller, which typically in the mathematical formulation has an extra differential term which counteracts the proportional change and offer faster rise time and less overshoot. Then we have the proportional integrated controller category, and Here, mathematically, the description of the control algorithm is based on an integral term that eliminates accumulated error but increases the overshoot. This is due to the integration. And then when the PD type of controllers and the PI type of controllers are merged into one single, which is the so-called PID controller, it combines the benefit of both, and this means that it is very widely, or perhaps the most widely spread controller type in the industry. And this is very frequently used also in the traditional part of cyber-physical systems. We can talk about a typical implementation of the feedback type of control, which is referred to as self-tuning adaptive control. And let me show the scheme of it, because I would like to use this scheme later on to explain that what other things can be done with the cyber physical system. So we first of all have a physical application sensor system, and this is extended with sensors which measure the performance, and the effectors are setting the system state. The control system provides inputs for the effectors, and the control system takes care of the keeping the system at the set operational point. So the sensors are measuring the output, and the effectors are producing control input for the system model, which describes the operation of the system. And then also performance specifications, what objectives should be fulfilled, what deviation from the objectives can be expected. They can be also inputted into the system model, and the system model based on performance indicators gives information to a performance evaluator, which is concretizing the behavioral deviation. And then this information is used by the intervention estimator, which works with parameter values and provides the control parameters to add certain kind of control gains to the system controller. So this is the self-tuning adaptive control mechanism. Why is it important? Because if we are talking about smart system operation, obviously the smartness should be considered, and the smartness has an influence on the operation. This is, for instance, what we have discussed, and the difference is that the runtime acquired data are put into a augmented system operation model, and then the information what is produced is used for development, operational structure development, and then a functional and structural adaptation and plan, and the intervention planner works accordingly. So this is how we get from the control of the simple systems with the feedback type to the smart system operation. It doesn't matter if the system processes one critical operational variables or multiple ones. Actually, the procedure is the same, and if we have multivariable control problem, then the same happens with a single variable control system case, and the differences are used as a means of control, and a kind of prescribed relationship is maintained between the different variables. And what is happening as an extra, that typically there is an optimization effort in the controller, which is trying to tries to achieve a kind of Pareto type optimization. The problem comes when the human is in the loop, and the cyber physical system operation obviously is not anymore based on pure system agents which are making the decisions and taking care for an autonomous control and the whole autonomous operation for the system. But when the human agents are in the loop, then we are talking about human in the loop control mechanism, and then it is typically a kind of supervisory control. That is why it is important for cyber physical systems. So the control of next generation cyber physical system is something what will be different. And let me show here a video. I hope it starts. Yes, which we received from the BMW, and this is a kind of concept on how to foresee the expectations of the self-driving of the car, and this shows a lot about the control need. Just see, for instance, obstacles will be on the road. It is coming. Here it is. So you didn't know it, but the control of the car should take it consider. Just please see the bicycle driver now. You cannot see it, but suddenly it appears. And then the control system should be aware of it. And then if you go further, for instance, with this sort of driving exercise, then you will see that that when you go to the automatic driving mode, then, for instance, you have to take care of people who might cross the road, not only just at designated places, but anywhere. So you might react incidentally to what happened. So obviously here we cannot see how to monitor these things with a pre-programmed or differential control mechanism. I believe we can stop here because the essential things were already mentioned. Let me come back to the presentation and to continue with a small message, what I would like to deliver to you, namely that here definitely the need for open loop control again appears, and it is not, however, the same as it happens with your electric toaster, which is also using a open loop control. The main issue there was that the output of the system is a kind of independent from the control action, and there is no state estimator. That's why your electric toaster may burn the bread. But obviously, the open loop control should appear in a different form, a different manifestation as a complex control task for next generation cyber physical system, and it should be equipped with anticipating capabilities. So the controller, the actuators, and the system itself should provide a kind of internal mechanism which is capable to do this anticipating. And obviously, it is a lot of information. It is about context processing and so on and so on. So this is most probably the reason why when we look at the autonomous vehicles. And then if you consider what they do for detection, reasoning, and actually in order to get to self-control, then it is a rather sophisticated model and actually cannot be covered as one as a whole. So this is why, for instance, different automation levels are defined, which are targeting different type of activities in the automated vehicle control. Here you will find a slide on the anticipating control systems. Actually, the issue with them, they are in their childhood, so there are anticipating control systems on the development, but there are far from being standardized and or used in serious industrial application context. So what is the most important, and that's why I stopped here, that they have dominant runtime learning capabilities, and therefore, actually, these sort of anticipating control systems are often called learning control systems. And they are connected according to the plan to self-adaptation mechanisms and historical learning mechanisms. Since the time for this block elapsed in a very fast way, I would like to call your attention to a couple of suggested literature, for instance, modern control systems for Richard and the co-editors Chang and Anderson to publish a very nice summary on the development of architecture for cyber physical control systems or deployment architecture. And then GIAN and the co-authors presented a good overview on fuzzy control system, the past, present, and future. I couldn't even talk about the fuzzy control in this particular block. Then the next is a self-adaptive system development method for smart control system in CPS, Chung and the other co-authors. And finally, Kubernetes paper, cyber physical security for industrial control systems and IoT, what I would like to offer to your attention. And here I stop sharing for a moment, come back to the panel, and although the time is advanced, do you have any comment? Do you have any question, please?
Hello, sir.
Yes, please.
The session was very nice, sir. Actually,
that morning, Dr. Vasanya.
Yes, sir. Yes, sir. The example of BMW was very fantastic, sir. Actually, it could recognize the objects and it could avoid the accidents if any. And it is the part of cyber physical systems, sir. I wanted to know that what can be the broad steps, for example, to identify certain flaw in a machine and to set alert for an operator. For example, it's automatic monitoring and controlling, feedback control. So, sir, I wanted to know what are the broad steps actually.
Yeah.
In any mechanical manufacturing process, for example, additive manufacturing or some lathe machine or like us.
If the line is somewhat broken today, as I discussed with Professor Gupta this morning, but if I understood the very essence of your question, you are asking me about how to forecast, how to see what happens, and how to incorporate in a control system. Yes. Yeah. So it is a complex thing because there are two approaches to that. One approach is that sort of physically based approach, which is actually was tested in the last 5, 6, 7 years, when you have LiDAR on top of the car, and then it creates a kind of comprehensive model, and you try to figure out what may be there. But you have to consider that it is a lot of data. It is very difficult to compute, and it is definitely something which is incomplete because you cannot detect anything. For instance, if something is in a shadow or something is behind, you cannot detect it. For this reason, there is another stream of the effort which is about the semantic reasoning. And it is not completely separate from the physicality, but at least it goes into a virtual domain in which logic and the logical processing play a role. I believe tomorrow the second lecture will be exactly about this, namely that context-based reasoning. How can we reason out things from data what we cannot see with the eyes, cannot see with the sensors, but can see with the mind that there might be something there. Because just consider, for instance, when you see when the car was passing a van which was standing. This is, for instance, a situation what you can describe with a rule that if there is a overtaking case where you don't have a full view on the scenery, then do this and this and this. So this is that sort of inferring, this is that sort of logical semantic reasoning what I'm talking about. And please, if you can join tomorrow in the second lecture, this will be my topic, exactly this is what I want to elaborate it. I apologize, it is very interesting that, as I told you, that the knowledge domain of cyber-physical systems is actually supra-dimensional. Whenever you ask me a question, I have to turn to a different field, because you were talking about or asking me about the control and the forecasting control and everything, and I had to go to the context-based reasoning because that gives the solution for me. So this is why, for me, this dealing with the cyber-physical system arena is just a wonder, but this is also the difficulty that we have to accept this extreme complexity and think accordingly, holistically. Thank you so much for your very nice question. Yeah, that's I believe the time is here for us to go further, and then I would like to go back to my presentation material, but beforehand, I believe I need to share the screen again. I did it. Please be so kind to confirm if you can see.
Yeah, it's coming.
Excellent. And then I'm going into the supervision and automation issues of smart cyber-physical systems. Let me say that it is a kind of continuation on what we just discussed based on the very good question what I received. So you remember there was a figure in the previous blog presented which made a differentiation between the control situation when the agent of the systems are taking care of the control, and that issue when the human is involved in the loop and the human may override the decision of the autonomous agent. This is actually the supervision, the sense of the supervision. But let's go into the theory a little bit to understand this problematic deeper. First of all, let's discuss what sort of human involvement can be in smart cyber-physical systems. For this purpose, I mean to explain it, I present you a kind of diagram which identifies four significant aspects. One is the role. So according to the role, the human involvement can be input provider, can be direct contributor or service customer. Input provider provides machine-readable input or provider of human interpreter input directly or indirectly. Direct contribution, information processor or operation actuator. Service customer, customer of passively delivered services, or customer of service needing physical interaction. Then the second aspect is the responsibility. What responsibility the human takes for the proper operation of the system? Is this responsibility accountable or unaccountable? The third one is the expertise. This was found very, very important because it is not all the same if an expert or a non-expert or even an outsider is faced with the system. So the expertise level influences also the involvement quality in the system. And then the intent, because the human has intent. And it can be cooperative, wants to work with the system, share of the system, or has some opposing intentions even with the system. So we have to see this whole picture when we are talking about human involvement, and this is what science explains. The second thing is the so-called level of automation. And there are different models for this. The most extensive, the 10-scale model, most probably you heard about it, it identifies 10 levels and identifies 3 domains for the human system operation. Let me mention the domains first. There is a domain which is a human control domain, and then there is a shared control domain and the system control domain. And these are just distributions of the task. For instance, just let me give an example. In the human control domain, for instance, human may do the whole job up to the point of turning it over to the system to implement. And for instance, in the system control domain, the system does the whole job and decides what the human should be told. So this is about how to communicate to the human beings in an automated manner. And any composition are that. So it is a rather complex picture with regards to the allocation of the task between the human and the system. But it plays a role because what I will present later on about the consideration of task allocation with regards to smart and the next generation cyber physical system is based on this. It is also important to see that in the literature, several levels of full autonomy were identified. For instance, the autonomy of decision. It means that the system independently examine the current situation, possible options, and their impact, take a decision, execute it, and monitor its result. Then the autonomy of exploration. For instance, the system independently analyze the present activity, explore the context, acquire new knowledge, and to look for handy opportunities. Then autonomy of goal setting. We are going high goal setting. So here the system should be evolving already. So sets on goals, use experience and interaction, prioritize actions to achieve them. This is something what I would allocate to the third generation cyber physical system. And then the autonomy of context framework setting. Decide to shift operational context and behavior changing context and create own ethical framework. This is really an extreme high level of autonomy, what is mentioned here. And then autonomy of replication. Don't forget that I mentioned that replication is an issue in case of the fourth generation system. The others are either adaptive or evolving, but direct replication is for them. So the system replicates itself, take actions leading to self-repair and acquiring the needed resources which are necessary for the replication. So here there is another view on the autonomy of the system. And then I would like to refer to the work of Clark, who actually presented a theory on the autonomous control levels by merging somehow these two things, those things which were presented in the previous two slides. So, and then he included also one more aspect, namely the space aspect, how the control happens, if it is based on interaction or if it happens without any interaction. And then he said that the autonomous control level 1 means a remotely piloted automated case, and the system is simply a remotely controlled machine for which the human operator makes all decisions. Please, to understand it, just consider a a drone, which is remotely controlled through a radio frequency controller at a remote distance. Then the ACI 2 to 5, these following four levels, are the so-called remotely operated. Here, human allows the system to do some part of the control, but the outer loop decisions are made by the human. What are the objectives that is depending on the human, like where to go and what to do once there, and the system may ask, on the other hand, permission to do tasks. Then on the next ACL level, 6 to 8, this is the next 4 actually, we can talk about remotely supervised application. Here, the human allows the system to execute its own task, only taking command if the system fails to properly execute the actual task. So this is the essence of the supervision here. And then obviously the last one, the fully autonomous operation, means that the system receives goals from the human and translates them into tasks. So here also the role of the human to ultimately specify what the system does or what the system is supposed to do is there, it remains there, so it is not completely separated autonomy, what we are talking about here with regards to the system, and especially not with regards to the next generation cyber physical system. But to make the sentence complete, let me utter it once more. So the system receives goals from human and translates them into tasks, which it does without human intervention. That's the important element of the automation, that the system automatically executes, and the system has authority to make all decisions in this particular case. So based on this, what we can import to our cyber system development exercise, and how can we make a system here, and how can we work according to this scheme. So let me build up a reasoning model. This reasoning model, first of all, starts out from the levels of automation, what we already discussed. Obviously, the system may have two forms. One, the system is not in the loop, so everything is done by the human. And we can go to the other extreme, which means that no human in the loop at all, the operational or the control loop, what I'm talking about. But in between, we have a useful domain, because these are just the extremes. And let me show you. So obviously, if we define the interaction between the human stakeholders and the cyber physical system, then we have a range of cooperative tasks which are to be executed. And then traditionally, actually, in our interpretation, the cyber physical system automation levels, the 0 level actually means, and this is typical, for instance, the traditional working culture of humans. The humans are the main executors of the task, direct task performance, we say, and they are just using tasks. But the tools are passive, and they don't have anything to do with the goal setting and the execution of the task. But then the second level, we have the system-assisted task performance. So the human is performing the task, but the system is assisting. So as you can see here, there is a different proportion allocation on this first level of automation with regards to the cooperative task execution. We can go further, and then we can put the human into the executive controller position. And what we can see here, that on this level of automation, then there is a balance achieved between what the system executes and what the human executes. And then if we go further, we can reach the supervisory controller level, then the system takes over gradually, and there is less typically supervising related task for the human. And then here is the strategic planner role. This is what was interpreted previously. So a system, or most probably a system of systems does the task. Multiple different heterogeneous systems are operating here. And the human is the strategy planner, set up the goals and creates a framework for the system operation. So this is the model what we a couple of years ago proposed for consideration of the task allocation of human stakeholders and system components or subsystems with regards to next generation cyber physical systems. And we can interpret these levels that actually what is happening that. So here the system is not considered for automation. Human executes a necessary operation. Control is provided predominantly by the human, and human-human interaction happens here only. Then, on the next level, the system presents limited automation. Human closes the loop of the operation as a kind of controller or controller of the output. The human performs control of the system actions and detects if there is any deviation with regards to the objectives. And there is a human system interaction in which the human is the initiator and the system is the performer. Then on the next level, the system is largely used already for automation. The human or system closing both of them can be in this role. So they close the loop of the operation, and the control is provided dominantly by the system, and system-human interaction is representative. See the change here. The initiatives here are made by the system. That's an important difference to the previous case. And then on this fourth level of automation, the system is actually who closes the loop of the operation. Only system components are taking part in the control. So human is acting as a strategy planner. Human may start or stop operation. System interaction is self-organized. So actually, this is why we can talk about here the system of system, because there is a system of system interaction is also organized here. So why is it important? Why we identify these four active levels here? Because we believe that this should be connected to the generation model of cyber physical system. So this is what is that sort of intelligent cyber physical system could do. This is what cognizant cyber physical system could do. And if the cognizant cyber physical systems are available, then we can talk about supervisory role of the human stakeholders. This is the current situation. We are working towards a kind of balanced comprehension and balanced allocation of the work of the system and the human, and we keep in the second generation system, or with regards to second generation system, the human in the executive controller position. Important issue is timing and predictability of the timing of the system, because this is also one important aspect. The time is very much up, and I would like to spare some time for questions. For this reason, I would like to recommend you to study Lee's work related to the timing of cyber-physical system, and his work is very much focused on, for instance, how to ensure that computation always finishes when guaranteed in or within guaranteed time windows. You remember that in the fire evacuation phase, this was one of the problems for us. And also his work suggests that we have to put our interest in worst case performance scenarios rather than the average performance scenario of the system. And we have to consider also the predictability of the timing, namely the time required by a system to perform an operation, and this should happen with little variation, and the timing and the scheduling of the system should be computable, because if it does extra time or takes extra time, that is negatively influences the overall output. And obviously, the timing should be in a way which is not influenced by other parallel operations in the system. So based on this, we can consider a kind of real-time computational and timing spectrum. We can have non-real-time, soft real-time, and hard real-time implementation, computer simulation, user interfaces, internet video, audio, telecommunication, flight control are representative examples for this. But this is the point when I have to stop, and I have to say that in my presentation, you will see many other slides, but obviously it is more than I could present at this very moment. But in the suggested literature, you can also find many other concepts about timing of the systems and the supervisory control and the control. For instance, this particular paper is very useful with regards to the modeling the types and levels of human interaction with automation. Then the next paper is talking about the stages and levels of automation. There is a third paper proposed here, human supervision and control in engineering and music. Interesting association, please read it. Then here is Edward Lee paper, the CPS foundations, in which the timing issue is addressed, and this multi-author paper, which is about automatic control system for high reliable CPS, is what I wanted to say. So this concludes this particular block, and before taking the questions, let me summarize what were presented in this session. It was about the control approaches in cyber-physical systems. This was the content of the first presentation. Then I called your attention to the fact that open loop control in a completely new form may play important role in next generation cyber-physical systems. The video showed cases where it is very important. And the second block dealt with automation and very tangentially with timing issues. So thank you for your attention for this part of the lecture. Stay tuned, and I stop sharing the screen, and I would like to ask the moderator to take questions, and I would be pleased to answer these questions.
Thank you, Professor Kunde. Any questions?
Hello, sir.
Yes, please.
Yeah, we will.
Sir, actually, I'm curious to know whether the role of sensor is that much important in developing a cyber physical system. For example, if we are executing some raw data, is it necessary to get it from sensors, or the available data is also means enough to analyze it?
I'm sorry, the line is so broken today. Can you please slowly repeat? I
Yes,
apologize because
sure, sir.
I really would like to understand correctly what you are asking, but I don't know what is with India today. The line is so broken. Hopefully you can hear me better and you can see me better. Please be so kind to repeat it.
Yes, sir. Yes, sir. Sir, I'm saying that whether these sensors, the role of sensor is that much important in developing a cyber physical system, because we are getting the data from sensors and then we compute it so as to execute some action in case of the cyber physical system. I'm asking whether the sensors only are important, or we can get it from in form of images with the help of a camera or like that.
So what is what is important? You said that if
Yes,
it
sir.
is
I'm talking about input. Yes, sir. Yes, sir. Is it necessary to get it from sensors only?
The question is that what is important, whether the sensor data is important or we can take this data from the images or camera.
Yes,
And other things.
Correct, correct.
sorry, the lines are completely broken now. My God, I cannot
No
hear
problem,
you.
sir. No problem.
Can you send it in the chat?
Chat box.
Sure,
Please
sir.
write
I will. I'm doing it, sir.
type it in the chat, please. Sorry for that. I don't know what's going on today. This morning I already observed when we were talking with Vijay that there is something wrong here, and it is just continuing. Sorry, can you type in the chat?
Yeah, just.
So now I see. So what is important sensor or images from a camera can do the job? See, okay. So so sensor or and in which context? What to detect? So what is important, sensor or images from camera? Obviously, the camera is a sensor in itself. So this is why I couldn't understand the question, because for me the camera is one particular sensor. The camera is producing a stream of frames. You can have a sensor, a light sensor, for instance, which a light sensor can detect, for instance, the intensity of the light, the frequency of the light, the color of the light. So the camera is a comprehensive, a complex sensor which is working with light. But a light sensor can do lower level tasks as well. So for me, when you ask which one is important, and that's why I was not sure if I can answer this question correctly. So please, it is, and I apologize for saying it this way, but for me, it is not a question which one is important. Both are important. Even using them together important, because maybe you can control this way each other, you know. So the sensor, a light sensor can be equally important in a particular application. Just consider when you measure, for instance, distance with a laser light. The detector which receives the reflected light is most important, because otherwise you cannot measure. But you cannot do it. You cannot do it with a camera. very good question anyway. I apologize for this problem with the sound and I don't know what to do. I will check my computer and restart the computer in the break because the break comes. Am I right, Vijay?
Yes.
So thank
Understood,
you.
sir. Thank you, sir.
Thank you so much for the
Yes.
thanks, and I hope that in the second part of the colleagues will come up with questions as well. Thank you. So let's keep at least 10 minutes break.
Yes, just we will take a screenshot, Professor. I request participants to turn on their cameras.
Okay, yeah, sure.
Yeah. Ruchika, Keshav, Mitlesh, Arun, Sanjay, Prashant.
Yes, sir. I see now the lady, but you said that we have two ladies. Welcome, lady.
Yeah, just a minute. Sunil Saket, Ruchika and Arun, your video is not on. Arun, Ruchika and Sunil. Okay, I think we are done. Okay, thank you, Professor.
Thank you so much.
And
then
we will meet after 10 minutes because we are already late.
My time.
Yeah.
Thank you so much. Thank
So,
you.
we will break for 10 minutes and at 3:15 sharp Indian time, we will meet.
Thank you.
Okay, thank you. Okay. Yeah. So, shall we start, Professor?
Alert from Microsoft Excel.
Yes, just a moment. I start sharing the screen
Yeah.
and I set up my presentation. Just a moment. Yes,
Yeah.
I'm ready to start.
Yes, you can start.
So you are recording.
Yeah, it is on.
Thank you.
Okay.
So the second lecture will be about the sensing and actuating technologies, which are very important elements of every cyber physical system, no matter if they are first, second, or third generation. And I also know that some of you dealing with sensing technologies and actuating technologies. I hope, nevertheless, that some new aspects, new issues will pop up in my presentation for you as well. Let's start with sensing and detecting technology. So we mentioned that cyber physical systems are supposed to penetrate into real life processes. They are supposed to detect what's going on in real life processes and to offer it for some sort of reasoning by the smart cyber physical system and according to what has been learned or what has been figured out, influence the real life process. Here, the input is obviously coming from sensors and sensor networks, and the actuation happens with effectors or effector platform. This is those sort of loops in which sensors and actuators are used in cyber physical systems. Let me show you many common everyday examples for sensors and actuators. They are built in. You may not see it, but an open, a automatic door or window, a environment regulator, lighting these cleaning devices, instruments, and these are all equipped with sensors, needless to say. So there are plenty of them. For this reason, we have to impose some sort of taxonomy. And the first aspect, according to which we would like to talk about the sensors, is the kinds of the sensors. And according to this, we can identify physical sensors, which convert the physical quantities such as light, sound, pressure, texture, and heat into electrical signals. We can identify chemical sensors, which play a role of taste and smell depending on the present and composition of the various chemicals it converts and detects electrical signals. Please don't forget that we are talking about experience, and the chemical sensors may play a role in that. Then we have biological sensors, which are considered to be part of the chemical sensors, but they are different in that they detect the states or substances using biological properties that emit electrical or optical signals. And we have sulfur sensors, which extract semantic information from action sequences or from data constructs while the computer is operating. These are the major kinds of sensors. And then we can talk about type of the sensors, which are obviously devices that monitor and measure one or more physical and virtual quantities. And the typical ones are accelerometers, scopes, magnetometers, cameras, chemical sensors, microphones, pressure sensors, rudder, lidar, strain gauges, and so on and so on. So fast repeat. The basics of the sensor is that any material or device that has the capability to detect an abstract or physical property can be a sensor and is a sensor. You have seen in the front image, most of today's project has multiple sensors already. They are typically classified according to their purposes, such as temperature sensing, proximity sensing, light, ultrasonic, gas sensing. The expected main characteristics sensors are high accuracy, low power consumption, inexpensive installation, and minimal maintenance needs. Sensors detect not only quantities, properties, or variations, but also activities, for instance, movement, fall, opening, opening the fridge, taking medicine, or blood pressure. These are important things in terms of embedding cyber-physical system sensors in human environment. I must tell, it is still challenging to approach the proper functioning of the five human sensory organs, namely the eye, the ear, the nose, the tongue, and the skin in general, and especially in interaction of the five. But in certain respects, sensors are going beyond the human capability. Just consider, for instance, ultra-red sensors, what we cannot detect with our eyes. So the next type of taxonomization of sensors is according to the GIAN. We could say that these are kinding or sorting into categories according to the operational parameters. We can talk about absolute sensor, just detect a stimulus in reference to an absolute scale. We can talk about relative sensor, which produce a signal that relates to a specific case. We can identify active sensors, which require external excitation and power. And we can talk about passive sensors, which generate electric signal without additional energy. And we can differentiate the genre of low sensitivity sensors, work in a sensitivity range of human sensors, and high sensitivity sensors, which detects effects but cannot be detected by the human sensors. I already mentioned an example for that, but the other example is, for instance, the magnetic radiation, magnetic dose or a radiation dose. The major characteristics of the sensors are summarized on this particular table. Different names of sensors are listed here on my table, and then the input quantities are there, and passive or active kind of sensors are identified, and the output quantity, voltage, current, resistance, or capacitance, or data are here. Actually, this shows the variety actually of the physical quantities what we can measure. We can see that passive and active sensor play an equal role, but it depends on the application what we prefer. And the output quantities can be as wide as the input quantities. If we go further, there is an error now. Sorry for that. If we go further with the discussion, then we have to mention that in addition to sensors, we have also transducers. Sensors convert any type of detected physical energy type of quantity into electric energy. Transducers, however, are converters that convert any type of energy into another one. Typically, an example is a loudspeaker. It receives electric signal, it creates a magnetic field, a varying magnetic field, and the varying magnetic field generates acoustic waves. The transducers are frequently combined with sensors. Here is what I wanted actually to mention, however, about this sort of transducer effect. Sometimes the information what we can get at the coupling of the sensor and the signal conditioning element is just a reaction and may not have meaningful information for us. Then, if we want to make a true difference between the sensors and the transducers, then on this table, we can see some differences. For instance, there is a difference already in the definition. A sensor, as defined earlier, a system device that senses and reacts to physical, chemical, biological, or logical conditions. The transducer as a system or device converts one form of energy into another and converts the data to electric energy. The function of a sensor is detect the physical quantity and produce an electric signal based on the amount of the quantity measured. The transducer converts the one energy to another. The sensing aspect to sensors mean that the detector element converts physical and logical quantity to electric values, while the transducer consists of a sensing element plus any associated circuitry, which conditions the signal so that it is strong enough for further processing in multiple stages. The feedback is also different. The sensor mainly measures a quantity and cannot give feedback to the fed system by itself, while transducers converge between any form of energy to produce feedback to the fed system. The transducer, for instance, the motor and the loudspeaker, output is always meaningful. Examples, pressure sensors, which might detect pressure and convert it into electric current, is an example for a sensor. And the transducer detects one or more energies, as, for instance, I mentioned the loudspeaker, but also, for instance, a electric cord can be mentioned as a kind of transducer. If we want to capture what the sensors do, we need to model them. And obviously, the change, what is introduced in the physical quantity, that is what we have to capture in a sensor model. But what is also important is the sensitivity of the sensor and the accuracy of the sensor. The major modeling issues are, for instance, physical dynamics, the noise and the noise level, the bias and the emergence of the bias, the sampling rates, the interactions, for instance, and the force. We can use linear and affine descriptive functions. The first one is the linear one. The second is a affine descriptive function for a sensor. Then the affine sensor model consists of a linear function plus a constant. This is what you can see above. But it can be also extended with, for instance, the bias and also the noise. So this way we can model the full operation of the sensors under environmental effects. The sensitivity specifies the degree to which the measurement changes when the physical quantity changes. For sensor modeling, we have different languages. This is what where I want to arrive at and talk about. But beforehand, I should mention that the current sensor systems are not standard, and we really need comprehensive sensor models in order to realize what the detect or represent what the detectors are doing in a cyber physical system. A sensor model should be a sophisticated software representation of how sensing and detection is happening with the system. Ad hoc integration of the sensor device, if it is not happening based on a systematic composition of the sensors and not guided by the model, may carry out pervasive detection tasks, usually in a form which is not necessarily favoring for us. For instance, we can end up with systems that lacks reliability, lacks openness, scalability, flexibility, portability, and interoperability. A seven-layer sensor modeling approach was introduced in order to enable the description of sensors right from the physical properties down to the end functionality. The seven-layer sensor model defines the sensor services which can interface seamlessly and work cooperatively with other enterprise applications. The seven-layer model has the following specifications for the layer. The first layer is the layer of interoperable data service description. The second layer is about the network communication and the protocol description. The third layer is the functional and operational description. The fourth layer is the event and protocol description. The fifth one is the unit and bulk description. The sixth one is the physical manifestation description. And the seventh is the operating environment description. So as you can see, the 7-layer sensor model actually connects the first layer, which is the cyber layer, with the pure infrastructural physical layer, which is the 7th layer. It is a systematization of the thinking of the use of multiple sensors in the system. There are so-called open use sensor models, and especially the Open Geospatial Consortium define a sensor web enablement framework in order to address specific interoperability challenges. The OGC specification come up with standards like sensor model language, sensor ML, observation and measurement schema, OMM, and transducer modeling language, TML. From these, the sensor ML specify models and provide XML encoding that provide a framework for definition of the geometric, dynamic, and observational characteristics of sensors in sensor systems. Different sensor types can all be supported through the definition of atomic process models and process chains. The transducer modeling language is aimed at to standardize an option for streaming multiplex data from a sensor system and for describing the system and its data encoding. Sensor languages actually commercially available, and they can be used to represent sensory data in the case of pervasive sensor methods. There are some representative languages, for instance, the IEEE 1451 transducer electric data sheet, the sensor ML specification, which is an XML-based sensor language, the device kit, the device description language, and the ECONET, energy conservation and home care method. All of them describe sensor data, but not all of them specify the process by which the sensor data is processed. The first two provide this opportunity. Sensor ML describes the sensor as elements of a process model, whereas their connections are shown as the process chain. Sensor ML specifies or can be used to specify complex data processing models. That's why it is often called data representation. If we want to know more about the mentioned sensor modeling languages, then we can see some information in this table. All of them are obviously useful for capturing sensor information. It would be a surprise if not, because they have been developed for this particular purpose. However, with regards to providing the protocol for communication with the information model, their relationship is important and very much different. For instance, the XML uses the DOM parser, the distributed object modeling parser. The IEEE 1451 communicates via through hardware and software with the text. The transducer ML uses XML and the DOM parser as the sensor ML. The same applies to the OM. ECONET uses a specific device specification protocol for this purpose, and while the device kit uses a generator to convert the device kit markup language to Java. The DDL, the design description language, generates a specific file which describes the data and the sensor information. So as you can see in the next column, they are all supporting sensor discovery, and they are differently supporting or not sensor data processing, direct processing of, or supporting direct processing of sensors. The sensor ML and the DBI are really supporting this activity. Then I mentioned the first place, the IEEE 1451 family. Actually, it is a general framework which focuses on smart and user interface. And briefly, let me show how this family builds up with the different elements, the different standards are included in it. You can look for these standards on the internet if you are further interested and see out what they mean. In the next slide, I summarize what these different elements of the family are able to do, and how can you use them for different purposes. The time constrains me to go through, but at least on the slide you can see. At the end of this block, I again would like to propose you some literature. For instance, the most fundamental book, new version came out recently, the Sensor Technology Handbook from Elsevier. This is actually a kind of starting book. Then the paper of Campbell and the co-authors on sensor technology in autonomous vehicles may give you important information about the recent development in sensor technology in this particular field. And there is another useful paper which is actually not up to date, but on the other hand, the basics are very well described. It is the sort of recommendation, sensor technology advances and future trends. You can actually check in this paper if what we have today is really in line what we had, let's say, 15, 16 years ago. Then there is an editor's book on smart sensor systems that I personally find very, very useful and also informative for the students. And the last one is the song and the co-authors papers on the IEEE 1451 Smart Sensor Digital Twin Federation for IoT and CPS research. That is the end of the first block, and then stop sharing and ask if there are any comment, question related to this brief overview. Obviously, in 25-30 minutes, not everything can be mentioned, but I believe the major key words are included in this, and you can use this keywords for searching topics on the internet and deepen your knowledge in those.
Okay, thank you.
Any comment?
Thank you, Professor. Any questions, anything, any comment, anything you want to do? Any of the participants? It seems no questions, Professor.
No problem. Maybe later on. Let's go further than the discussion, and I share my screen again, and we can go on with the recording. So the next part is the last block for today is about actuator and effector technologies, and let's start with the actual actuating technologies and the fundamentals of actuators. Let me present some definitions concerning actuators first. So actuators do work in the physical domain, while sensors may work in the physical domain, but may also work in the cyber domain. Just consider the software sensor, for instance. A software sensor, for instance, detects how many times the same person from the identical IP address visits a website, and based on this frequency can suggest how to relate to this particular visitor. But coming back to the actuators, it is a system or a device that changes the operational states and attributes of a system. The sensors are not doing it. Actuators typically implement controlled energy conversion. The input energy can be electric, magnetic, hydraulic, pneumatic, thermal, piezoelectric, whatever. The output can be some sort of physical effect, for instance, linear motion, rotating motion, speed change, force change, vibration, sound, light, and so on. Typical examples for actuators are like solenoids, hydraulic cylinders, pneumatic motors, linear micro actuators, stepper motors, displays, LEDs, lasers, loudspeakers, switches, valves, and so on. The effects of the actuators made are typically connected to the control system, and through the control system, these effects of the actuators are related to the system components or to the environment that they want to change. Typically, actuators are effectuating change in the actual state of the system. They may concern not only state, however, but also take some action. For instance, speak of a reminder, report an alarm, turn heating on, or record a program. So it is a concrete action what is done, or these are concrete actions which are done by a actuator. As output components, actuator may also alter the surroundings. Some typical examples of the actuator actions are, for instance, adding lighting, heat, sound, controlling motors to move objects, and displaying messages. The goal of the actuators is originate from the definition, convert cyber data to a physical phenomenon, and this way they are complementary opposite to sensors. They are usually classified according to their working principles, such as hydraulic, mechanical, electric, and so on. Recent studies show that wireless actuators are very promising. They can be utilized even in industrial, not just laboratory, but also in industrial environments where real-time applications take place. However, the new technologies and methods are required to overcome the existing challenges. For instance, the problems with the wireless network and with the loadability issues of the sensor. So, accepting wireless actuators as reliable for performing industrial tasks is still an issue. A specific kind of actuators are effectors, which I would like to discuss by definition. They may be friction-based grasping manipulators, which can change from simple parallel jaw grippers to multi-finger manipulators. Simple models of these end effectors require less grasp analysis but may provide worse grasp. These are very important issues for instance, the robotic industry, where the friction-based grasping manipulations are very often happening. But to avoid the mentioned issues, more frequently multi-contact point hand manipulators are also used. With more fingers, we can apply more contact points and we can also achieve planar contact with the object. Assuming the friction, with more contact, we can increase the chance of a stable force closure grasp. The end effectors have four different types of effect mechanisms. The first one is the impactive. Jaws are closed physically grasped by direct impact upon the object. Rigid body, hollow object, can see. The other one is the ingressive effect mechanism. Pins, needles, and tackles physically penetrate into the surface of the soft object. This is happening, for instance, with textile or cardboard. Then a restrictive effect mechanism, attraction, suction force applied to magnet vacuum to object surface. This can be used for manipulating sheets, plastic sheets or paper sheets, but also glass tables. And then the contiguity is the fourth one, which is a kind of direct contact that takes place by a fusion to the surface. This is, for instance, temporal gluing, increasing surface tension, or, for instance, freezing two objects together and providing the necessary effect, lifting or hoisting effect this way. Specific category here are the grippers, which are end effectors used to grasp, snag, hold, and manipulate three-dimensional objects, manufacturing parts, if you like, during work tasks. Grippers are often deemed to be mechanical hands together with hooks, magnets, and suction devices. Grippers subject to point-to-point control. Each pass the robot takes between where it picks up and puts down should be specified. Grippers should be designed to require a minimum amount of maneuvering in order to grip the workpiece. Typical application of grippers are machine loading and unloading. It is in the manufacturing industry a kind of common sense thing. Picking and placing of parts on conveyors, material handling, bottle handling, arranging parts, and so on. The function of the grippers are, however, useful in home context. And for instance, when we consider home care application of smart fiber physical system, we have to count on grippers, and we can use grippers for many simple tasks. The main features of the grippers can be summarized the following way. We can differentiate unilateral or multilateral gripping effect. So one unilateral or multiple. Unilateral grippers touching the handled object only at one point or surface. Examples, for instance, electromagnetic gripper, vacuum pad, and vacuum pad gripper. Multilateral grippers touching the handled object more than 2 points or surface. Examples for that are mechanical multi-finger gripper or multi-head pneumatic gripper. Some examples of the effector, for instance, here there is a well-known commercialized effector. Actually, This effector is called the direct hand, and this is a typical multi-contact point hand manipulator, and it is a highly flexible manipulator. On the other hand, it is it is with an overhead, namely a high computing cost, which is associated with the grasp analysis and actuation of the grasp. It is very much dependent on the sensor data because the touching cannot be better than what is described by the sensor data. Is appropriate for delicate and highly manipulative scenarios. Since we are approaching again the end of this block, and I would like to ask your opinion about what I presented, and especially if you are really dealing with these things and what aspect of these things are you dealing with. But before closing, let me again mention a couple of items from the literature which I believe will be useful for your future study. There is a book published by Springer which is fully dedicated to the actuators. Unfortunately, I'm not aware of any recent version, but this 2004 version is very comprehensive. For actuation purposes in manipulative flows, active flows, there is a paper which tells a lot about the challenges and the solutions actuators for active flow control is the title. Then Boulder and NASA presented a paper on linear electric actuators and generators. It is still valid and the basic principles are very well described. There is a somewhat more recent paper from Japanese authors on shock actuators. This is also a item that I suggest to study, and then a field which might be important in a social and human application of cyber-physical system is based on piezoelectric actuators and motors. And I must tell you that one of my graduating students, for instance, used piezoelectric actuators to transfer information about surface smoothness and surface softness and surface pattern remotely, and this was a kind of complex sensor for a, let's say, for cyber-physical system what she developed. That concludes this presentation today, and let's summarize what we were talking about. So the first block tried to give a general overview of the sensor technology from the point of view of using sensors in cyber-physical systems. And the second block addressed the issue of actuators and their possible use in cyber-physical systems. Thank you for this attention. This concludes the today presentation. I would like to come back to the mosaic and let me ask now that are there colleagues who are experts on this field, who are on a daily basis doing research or development in the field of actuators or sensors, or for instance, what controllers, for instance, just to get to know a little bit each other. That's why I initiate this discussion and putting the question at home. So is there anyone who is expert in this field?
Any questions?
No questions, sir. Thank you, sir.
Yeah, it was a nice lecture, Professor, actually. There are so many sensors, and then you have to select the one according to your requirement. So that is also a challenge, actually.
Yes. If no question, then obviously tomorrow we will have one, and we will talk about big data, massive data management issues related to cyber physical systems. And I also will elaborate a little bit on the blockchain technology, but not from cryptocurrency point of view, but as a safe solution for managing information between the actual nodes of a cyber physical system. This will be the topic for the first lecture tomorrow. And then in the second lecture, I would like to deal with the context modeling and context-based reasoning issues, which were already explored as important elements of cyber physical system development. So thank you for the attention today.
Just we will take one screenshot. So I asked participants to turn on their video. Sunil, Prashant, Ruchika, Arun Sharma, Mandloy, Prashant Sharma, Arun Sharma, Swati.
How can it be that certain attendees are multiple times recorded or appearing multiple times?
I could not hear. Just repeat, Professor.
Yeah, so I see that certain attendees are multiple times connected. Am I right?
Video is first time. Their video was not on for some of the candidates.
Okay.
Right. Okay, thank you. Thank you very much.
Thank you very much.
So we will be meeting at 4:30 for the lab session. And Professor, we will be meeting tomorrow.
Yes.
Morning your time.
Thank you so much. Have a useful afternoon. Bye-bye for now.
Thank you.
Bye-bye.
So we will meet at 4:30 today for the lab session, right?